All righty. Let's see. So I did some sample exercises out of 3.1, put those videos up. Sent out the thing about an exam. I'll try to get more to you soon. I'm not exactly sure what soon means, but just so you have, it'll go up through 3.3. We aren't doing 3.2, so we've had the 3.1 stuff. We'll talk about 3.3 today. I'll get some videos up on problems, that kind of thing. So it'll go up through 3.3. And then we'll have, of course, class on Monday, and you can ask questions and so forth at that time. If there are no questions about anything, I just move on. I just keep going. But you will then, after class, I will go sit down and make available the exam. It's take home. Really the only real rule to it is you don't get to use human interaction to answer questions. Now, human interaction can be texts and things like that. That is still human interaction. So you can't talk to anyone else about the exam other than me, because I like to feel important that way, I guess. And but I figured a good way to do it with the way the classes are working and all that is I'll give it to you Monday. You turn it in Thursday or by Thursday before class, and we'll kind of look at it that way. And let's see. So and then because of that window in there, I've pushed the due dates a little into the next week. We'll probably be able to make that up just fine. And I think that's what I have on where we are. And as I say, I'll start talking about 3.3 today. Questions on any problems? Anything at all? Yes?
It's just like 35 and 3.1.
3.1, 35? Yeah, okay. So the mean value theorem. Okay, so on 35, it says, consider the graph of minus x squared plus 5. So f of x is equal to minus x squared plus 5. And let's see, on the next page, yeah, okay. And it says, find the equation of the secant line joining the points minus 1, 4 and 2, 1.
I think it's a different one.
Wait, I'm looking at 3.2. I was thinking, why did I assign something on the mean value theorem? Ha! I didn't. Yeah, sorry. 35. Oh, yeah, that looks much better. Okay, y equals 3 cosine x from 0 to 2 pi. And we are looking for the absolute extrema on that interval. Makes much more sense. I like this much better. Okay, so 35. Y equals whatever it said, 3 cosine theta. On the interval 0 to 2 pi, and that was a closed interval, correct? Yes, that's what it says. and we want to find all the absolute extrema. So generally speaking, probably what you want to do, you don't necessarily have to do things in some of these in any particular order. So for instance, I could evaluate the function at 0 and 2 pi to start with, because I need to do that at some point. But typically though, usually when you start thinking about finding extrema, the first thing I usually think about, and probably you should think about, is just finding those critical numbers. And so for our critical numbers, we want to take the derivative. So y prime is minus 3 sine of theta. And we want to set that equal to 0. And we're only interested between 0 and 2 pi. And so for sine, that is 0 at 0, and at pi, and at 2 pi. Okay, so we would have sine theta is equal to 0. And so generally speaking, again, theta could be any integer times pi. And so k is an element. What's the symbol for integers? Anybody know? Yeah, it's the z thing, right? So it's, some sort of big typeface z for all the integers. And so we have, this is our possible answer, but we have to be between 0 and 2 pi. And so in our case, we could have theta equal 0, theta equal pi, or theta equal 2 pi. So we're stuck with those on this closed interval. So that's interesting in that they haven't given you many problems where the endpoints of the interval are also critical numbers. So, so we have that. And now at this point, since we have all our candidate, in this case, theta values, which again, it's kind of strange in this case that both endpoints are also critical numbers. But all I really am doing in this first step of finding critical numbers is adding to those two endpoints of all the endpoints I want to, or sorry, all the points I want to check. And so then I just check them all. And so in this case, I have y of 0 is 3 cosine of 0. And that is, well, cosine of 0 is 1. And so I get 3. And y of pi is 3 cosine pi. Cosine of pi is negative 1, and so we get negative 3. And then y at 2 pi. Now, since, in some ways, I don't necessarily need to even do this. I don't remember what the... yeah, it says find the absolute extrema of the function. Because here we get 3 cosine of 2 pi. I suppose, knowing the cosine function and so forth, knowing that I had, a value of 1 here and a value of negative 1 there, I'm not sure I really had to even check this at this point. Because if I just want to know what that maximum value is and the minimum value, I don't necessarily need to even check this. But I have that for 3. And so I have a tie at the two endpoints. And actually, that's a good question. I'm just looking to make sure. that my definition is the same. Yeah. So, this is just a definitional thing. The extrema are 3 and negative 3. They're just the values of the function, those maximum and minimum values. And so they're not the collection of the point, right? If I was asking for all extreme points, or the extreme points, then I would say you really do need to use 0 and 3, and then 2 pi and 3, both of them, okay? Because those are different. 0, 3 is different than 2 pi 3. But the textbook's definition of extrema are just the y values. And so you could just say, the maximum is 3 and the minimum is negative 3. And you could leave it at that. If you wrote like 0, 3 as your maximum, 0, 3 in parentheses is your maximum, actually I'd be okay with that. That's fine. I'd probably make a little note, but not a big deal. If you wrote the maximum is 0, well, that's just wrong, though. Okay, the maximum occurs at theta equals 0, but it is not 0. More questions on that or anything? No? Okay. Other questions on the material? Nope. Okay. All right. Well, so in 3.1, we were looking generally on closed intervals, which makes our job a little easier. Okay, because on a closed interval, I truly can just get a list of x values and try them all out in the function. Now, I suppose I could come up with a function that had an infinite number of x values with relative extrema, and then that's a problem trying to check each one. But for the most part, right, I have some a, some b, and I have this function that no matter what it does, I'm going to look at that point, that one, that one, that one, and that one. Okay? And it's got to be one of those. Right? Because, again, at these local maximums or relative maximums, well, that is a maximum there, and so anything close to it, it's bigger than that, and so you could say, well, there's its neighborhood, and there's that one's neighborhood. Well, how do I know it didn't peak up in the middle? Well, because my only other critical number in between them is that one, and so it's either bigger or smaller than those, and and everything in between is fine. And so I really have just this usually finite number of things to check. So I get the critical numbers. Those are everything inside here usually, but again, in that case, we had some hit right at the end points. So we get the critical numbers, we check the endpoints, we just check all of those. Pretty much, which one's the biggest, which one's the smallest, and there you go. I'm done. Okay. On an open interval, life gets much, much harder, relatively. Well, actually, I guess, yeah, it can get quite a bit harder. Because the problem is, on an open interval, so if this is A and that's B, you know, I have something like that, and if I don't actually have the endpoints, then again, I'll just, you know, I'll take something relatively simple like that, but that's open. Okay, now, as I look at something like that, well, I don't really have a point to check over here, and don't really have a point to check over there, and so now, you know, okay, I get this point, I get that point, I get those critical numbers in there, and I check them, and I say, oh, you know, okay, is this one taller than that one, you know? So I say, oh yeah, there's the maximum, there's the min. Well, actually that's not true for either one of those on that open interval. Because all of these points up here have higher y values than that does, and a few of these, you know, all these in here have lower ones than that. And so they are relative extrema, but they're not the max or min on that open interval. And, you know, this wasn't a case where I drew these as asymptotes or anything like that. It's just, it's an open interval. So it can get kind of messy to deal with that. Now, in our text, pretty much what they ask for is just, let's characterize, let's know whether this is a maximum or a minimum, and so forth. And, well, even that can get a little rough because, you know, once again, taking this, oh, that doesn't seem so bad. You know, this one is taller than that one, so that must be the maximum, that must be the minimum, the relative max and min. Okay, well, maybe, right? Because if I change the picture a little bit where, well, I don't know, maybe this is cheating in this case, but because I have the function undefined right there. So really this is two intervals, but let's say, you know, we didn't really find that until we were looking for critical numbers, so maybe we found a critical number there as well. You know, this one's taller than that one, but that's a relative minimum and that's a relative maximum. So, you know, it doesn't, just because one's taller than another doesn't mean, you know, squat when it comes down to it. We have to have some way of checking. And again, graphing, well, it's pretty obvious, right? If I'm looking at the picture, it's easy. No problem. I can do it. But the question is, can you do it without looking at the picture? And that's really, you know, that's a big key for getting things done automatically or, you know, autonomously, you know, where we can give it to a computer and tell it to just go do something. It needs to be able to find these things and know whether it has a relative max or a relative min. You know, so what are the characteristics of such things? And 3.3 and then 3.4, they're just giving us ways to check. Okay, so you know, so again, you know, okay, let's just take a maximum. You know, one of the things we noticed was right here, right, f prime of x was equal to 0. And then as we, make sure that's in. Yeah, okay. I have a little question mark on my network thing, but let me switch over just real quick. Yep, okay. Just making sure you all were still with us. Okay. Okay, so, we already came up with this condition, or undefined, but for nice smooth functions. Smooth usually means, in math sense, derivatives are there. So in nice smooth functions, yeah, f prime is 0, the derivative is equal to 0 at that particular x value. And then what else do we notice is, well, if this is a maximum, I'm going up there, okay, so it's increasing. The function is, so I'll say f of x is increasing there, and f of x is decreasing here. So visually, that's what we see, and we can talk about it. But then how do we know that, how do we check that in the mathematics? And, well, this is one of those funny things. I mean, you've been talking about slopes since, you learned some algebra. Slopes and increasing, so positive slope means increasing. Well, in the end, because a derivative is simply the slope of a tangent line, then we would have that f prime of x is greater than 0 over here, and f prime of x is less than 0 over there, because it's the slopes of its tangent lines would be positive on the right there and negative on the left. Wait, sorry, I'm facing the wrong way. Positive on the left, see, I got to turn around. It's like teaching kindergarten or something. Right, kindergarten, you got to learn to do things like, okay, everybody raise your right hand, and it would be difficult. Yeah, on the left we have the positive derivative. On the right we have the negative derivative. And similarly, if we have a minimum, then again we know we've got either the derivative's undefined here or 0. And then what we would hope is over here that f prime of x is less than 0. In other words, it's defined, so we could check that. And over here, f prime of x is greater than 0. And so we want to use that. We can check that. So given a problem, so that's pretty much they call what we're doing, what we're going to be doing the first derivative test, and so let's do let's look at their example 4 to start with. Okay, in the text, and they're looking at a function f of x equals x to the 4th plus 1 over x squared, I think. Yes, over x squared. And they say, well, find all the relative extrema. Okay, so we start it the same way. We just, if we're trying to find relative extrema, we look for critical numbers. And so looking for those critical numbers, I need to take the derivative. Now, I don't want to take the derivative of that. I mean, that, having it look like that, because that's a quotient rule. That looks too hard for me. I don't want to do that. So I'll set this over the denominator separately. Okay, all right, that's how I add fractions, get the same denominator, and then you add the numerators. So I do that, and then I simplify those. So that's x squared plus, and I'll just write that as x to the negative 2, and now I don't have to worry about a quotient rule or a product rule or something like that. And so I take f prime of x is equal to, well, 2x for the first one, and then plus, and I have to bring down the negative 2, x, and then I have to subtract 1, so I get a negative 3 like that. And I would like to set that equal to 0. And look for all the cases where this could be 0, and also where it might be undefined. And so what I have here is 2x minus 2 over x cubed is equal to 0. Now, if x is 0, I've got a problem, so it's undefined. So I found one critical number. I'll write that down in a minute. But if x is not 0, this is fine, and so I could multiply everything through by x cubed to get rid of that denominator. So when I multiply everything through by x cubed, I would have 2x to the 4th minus 2 is equal to 0. That's convenient, so divide everything by 2, pull the 2 out. X to the 4th minus 1 is equal to 0, and divide everything by 2. I get x to the 4th minus 1 equals 0. And so now, well, x is 1 or negative 1. And so x to the 4th equals 1, so x equals plus or minus 1. So those are critical numbers from this equation. Also, x equals 0 since, and actually I could see that way up here. I didn't need the derivative to know that the derivative was undefined at 0 because the function's not even defined at 0. Since, and you know, I could, I guess, write it as actually since f of 0, not f prime, but just even f of 0. Well, maybe I'll go with the derivative, since that's what they use in the book. F of prime of 0 is undefined. Okay. So we have 3 critical numbers. And now, it really is sort of an algebra, I don't know if it's algebra 1 or algebra 2 problem. What we have is that for the derivative, whoops, I didn't do that, or I needed to, did I? There's 1, there's 0, there's negative 1. And so if we're thinking about f prime of x here, well, I know it's 0 there, undefined here, and so I just need to figure out what it is in these 4 spots. And by what it is, I just need to know whether it's positive or negative. Okay? Because it can't change anywhere else. Okay, because it's defined everywhere. We're assuming it's continuous everywhere that it's defined, and you know, you actually should check that. But if it's not, then there's a possibility the derivative wasn't defined there anyway, and so it would have been a critical number. But so I've got these four places, and all I need to know then is something in between them. But see, this is back in algebra. When you were first learning algebra, you were given maybe a product of something, you know, maybe or you might have been given a quadratic or a cubic or something, some polynomial that you were supposed to factor, and then you looked at each factor to decide whether it was positive or negative, and, you know, that might have been for solving inequalities, something like that. You know, so if you had a polynomial is less than or equal to 0, right? The idea was you factored it, got the factors, and decided, you know, because it was 0 at those, wherever it factored, and you just then looked, was it plus, minus, in between, but you didn't look at every value in between, you just needed one value in between. Okay, and that's the continuity working for us. And so I can, you know, I could go here and just ask, well, what's f prime of, say, -2? And here, you know, what's f prime of -1/2? What's f prime of 1/2? And maybe what's f prime of 2? I'll just look at each of those and see what I get. And so here's f prime. If I want f prime of -2, I'll get what? -4 minus 2 over -8. Okay, so that's not really a plus, but it's -4 plus something less than 1. Oh, this is negative. So this is less than 0. Oh, that's a -1. So we've got negative in there. Now if I do it with -1/2, I get -1. And then once again, minus 2 over -1/2 cubed. Well, so that's 8. -1/8. Invert and multiply, I get a positive 16 plus the -1 or -1 is 15. And so that's greater than 0. That's a plus in there. F prime of 1/2, I get 1, and then minus 2 over 1/8. And so again, that's a 16, but it's -16 in this case. And so -16 plus 1 is -15. That's less than 0. That's a minus. And then finally 2, I get 4 minus 2 over 8. And that is greater than 0 again. And so there's a plus. So I can see the derivative does this, and what that tells me is, in this case, at both of my critical numbers where the derivative is 0, I have relative minimums. Okay, because you can go a little further with this and draw. You can say, oh, okay, I've got a negative slope. I got a positive slope. I got a negative slope. I got a positive slope. Minimums, both of them. Okay. Now here, well, positive, you know, positive slope coming in there, negative slope there. I might say, oh, you know, I might look at that and go, oh, there's a relative maximum. But no, the function's not defined there. Okay, so you got to be careful. You know, but the function is defined here, and we got a slope coming down like that, and then going back up. We've got 2 relative minimums and no maximums. Okay, so relative minimums at x equal -1 and 1. And then f of -1, that was 2 times -1 minus 2 over -1 cubed. And so, oh, it's 0. Wait, was it cubed or squared? Oh, I was doing the derivative. Never mind. Of course I get 0. No, okay. -1 to the 4th plus 1 over -1 squared. That's better. There's the function. So 1 plus 1 is 2 over 1, I get 2. And then similarly, f of 1 is equal to 1 to the 4th plus 1 over 1 squared, and that is also 2. And those are our values of those relative minimums. Questions on that? Oh, and that's what they got in the book, so that's good. It's always worth a check. No questions? Okay, so that's the idea. In the end, so what makes it really hard, or what makes a hard problem? Well, one thing that can make a hard problem is if the derivative is just really complicated. Oh yeah, just taking the derivative could be complicated. So that step could be complicated, could make it hard. Then, once you have that derivative, well, we need to find the critical numbers, so we have to set it equal to 0. We have to look for where things are undefined. Typically, the big thing there as far as undefined, just remember to check. Okay, usually, checking where it's undefined is not too hard. If you remember to check, it's not that hard to do it. So then solving for those points. And then sometimes it can be actually kind of difficult to evaluate the derivative, the derivative at in-between points to determine whether it's positive or negative. Okay, so that can be a bit of a hassle. But it's always those same steps. Okay, so we're always just looking at where the derivative is 0 or undefined, and then asking what happens in between, and that gives us a pretty good idea of what everything looks like. Again, I think I've showed you this on Desmos. I've got Desmos here somewhere. So on Desmos, I can put in that function f of x, and that was equal to x to the 4th plus 1, and then all divided by, so I'll highlight all that, hit the divided by x squared. So there's our picture. Okay, so we have that, and definitely it appears that we have this vertical asymptote at x equals 0. But then I can, hard to see that. I can just say f prime of x, and there's my derivative, and I can look down here and look to see, where it's 0, and there's that 1 and minus 1. So Desmos does a great job with something like this. And then, it's that blue line. I can also see that it is negative on the left side of -1 and positive on the right side of -1. And I can see the same thing then at 1. So I can see every value of the derivative in something like Desmos and just get it that way. Another technology is Sage Cell. We haven't done as much with that. It's a little more learning curve to do Sage Cell, but again, pretty much, I just need to tell it that I am using a symbolic variable, and I do that by saying var and space and x in there. Now, if I have more variables, I just put commas in, but x, comma y, comma z, comma whatever. And then I can put in my function. Now, with the function in this case, you don't need the of x part. You just, f. And you need to be a little more worried about the typesetting and that kind of thing. So I will put parentheses around it. I have x to the 4th plus 1, and then all divided by x squared. So I've defined that. And now, if I just want the derivative, I could just say like f prime, fp is equal to f dot diff, and say of x, the parentheses with the x is just saying, well, take the derivative with respect to what? Okay, because I could actually put like an a in there or something that is a constant, a parameter. And now, if I hit evaluate on that, it won't show me anything, most likely. I have to actually tell it to print or show or display. That's another word you can use. I like show, and so I'll say show FP. And if I come down here and hit evaluate, and if I typed it in right, then there we go. There's the derivative. Isn't that awesome? Right? And I could evaluate that derivative at points. Now, and I could actually go back and forth between this output from the Sage cell and put it into Desmos and look at the graph. Now, you can graph within the Sage cell and so forth, and we probably will. But Desmos is so darn easy to graph things in. So we could do that. And if I need more derivatives, so we can do the second derivative, third derivative, all I have to do is put a comma and tell it, oh, I want the second derivative. And it's that simple. And I say evaluate, and I get that. Now, is that the way I want it to look? Maybe, maybe not. So there are other things one can do to try to get Sage math to simplify things the way you want. You can say things like expand, okay, to multiply everything out. You can say things like simplify to try to get everything to pull together. It even has stuff like collect. So you can collect a variable or an expression. We aren't going to really worry about that right at the moment. I just want to show you that you can calculate derivatives really easily this way. Actually, you can also. Okay, so we've got our derivative there. Now we'd like to set it equal to 0 and solve for x, right? So let's try. So some of these things I get rusty on really quickly as far as what you actually have to do. But I think all we have to do is say solve. Well, we'll have to give it a name. So I'll call it solution, but just SOL, because if I'm wrong, maybe I am. And so solve, and we've got FP equals equals. You have to do two equals for a real live equal. 0. And then I think I just put in here comma and x to tell it what to solve for. And then if I did that right, I should be able to show the solution. And so we'll evaluate. And look at that. It even gave the imaginary answers, but it gave x equal -1 and x equal 1, as well as I and negative I. Pretty nifty. And you know, you can still definitely make mistakes, calculation mistakes, using the technology and so forth. But in some ways, there's almost no excuse, for not being able to solve an equation or something like that. You know, because again, you could do it numerically with Desmos. You know, again, Desmos, we did the same thing. You know, f prime of x here, we graphed it, and by looking at those x-intercepts, we set it equal to 0 and found x at -1 and 1. So there are a lot of ways to do the, I'm going to call it mindless calculation. It's absolutely not truly mindless. It may be mind-numbing at times, I guess, but we can, we've got plenty of ways in our technology to calculate things, to compute or calculate derivatives, to set them equal to 0, and all that. Now, one little technical note. You see, the way it gave the answers down there, it gave them as a list in these square brackets. It gave them as a list, and it gave them as equations. You know, it said x equals 1 or x equals -1. So actually, if you wanted to use those somehow, right, if I wanted to look at what's f of 1, so if I said show f of, well, the question is, how do I get to that 1 or that -1 or something like that, you know? And, oh yeah, that's not necessarily so easy, right? And now, I could just read them and put in f of 1, right? It's not going to work, so if I just do something like this, okay, it turns out, so this is where Desmos is a little nicer. I lied to you. I didn't know I was lying. It did work. I didn't think it would. Okay, so it worked. Yeah, that's nice. You know, but how would you pull that right off of there? You actually have to do a couple steps. So notice that if I wanted the 1, it's the fourth item. X equals 1 is the fourth item in the list. But you got to start counting at 0. So it's actually item number 3. There's item number 0, 1, 2, and 3. And so, you know, I could go in here and say, okay, I want item number 3 out of that. And if I hit evaluate, it should, yeah, say x equals 1. But the problem is, you don't put x equals 1 into f, right? You put 1 in. And so you can go a little further and say, well, it's an equation. X equals something. I just want, and you'd put a dot, and you'd say, right-hand side, RHS, and, open and close parentheses. So see, there's a little more of a learning curve. It's not real deep. You're just telling, I want the right-hand side. Oh, okay. But that should return simply a 1. And it does. So it's just Desmos, you know, that's where, if you can work within Desmos to do things, it's just way simpler. But the Sage isn't too bad. Okay, and so to, to do all that, it really, I mean, relatively speaking, given that there are 7 lines there and 3 of them are really about just showing a result, 4 lines to kind of get things done is not much, considering what we're doing here. Okay, so there's our intro to 3.3. I'll try to get some more solved exercises up, and I'll also be working on giving you a heads up on the first exam. But again, you'll get that Monday. It'll open up as a PDF on Blackboard, and then you'll just, again, take pictures or whatever of your solutions, make sure they're readable, and upload that stuff as a way to turn it in. Okay? All right. Well, I will see you on Monday then.